So yes, the lecture has also, the recording is started. So what I was saying here, that we saw that you can give a diversity gain of L provided you look up till n plus L minus 1 times for providing diversity gain for x of n, but for providing x diversity gain for 1 up till x of n, you have to look up from 1 up till n plus L minus 1. Now, remember here that how can I implement by maximum likelihood sequence detector? If you notice up till this time, or let us say before rake receiver, we were actually considering a single symbol being transferred. For example, in previous antenna diversity and time diversity, we were actually considering diversity for a single symbol. Here we were also considering for a single symbol, but at the same time we will need to learn about MLSD. Alright, so if you could see here, the first maximum likelihood sequence detector. So one is symbol detector. The other point is sequence detection, this MLSD. All right. So we were actually analyzing for MLSD. Why? Why MLSD? Because you could see that we were comparing XA with XB. Remember, where XA was a sequence, a vector sequence. XB was also a sequence. So we were detecting the sequence in one time. In one go, we were now detecting a full-fledged sequence. All right. So that is why our detection will be called maximum likelihood sequence detection. So we saw all of that, and it can provide this much gain. So how can we implement this maximum likelihood sequence detection? So first of all, I will try to explain with this explanation given by this book. But this explanation is, if you will observe, is quite generalized, or a very summarized view is given. Many of the steps are missing. For explanation of those steps, we will go to the famous book of digital communication, Fundamentals and Applications by Saklar. So many of you might have studied Saklar in your undergrad analog or digital communication courses. So we will refer to Viterbi algorithm from that book. We could have referred to from digital communication book, but I found the mathematics to be quite involved in the digital communication book of John Procase. Here we do not need that involved mathematics. Okay, we don't want to go into too much code design. We just want to see how can it provide us the diversity gain. How does a sequence detection work, especially for the very, very famous Viterbi algorithm? So we can go up to any undergraduate book and just learn the basics so that we understand that for communication in every type of ISI channel, in almost every, why this Viterbi algorithm is the optimum solution. So first of all, let us go through this book. So let us say I have a receive vector y. So I have a sequence x, which can become xa or xb, depending on which percent. So its corresponding matrix will be xa, xb, and we have seen that it can give us this much gain. Now the MLSD problem says SD problem says that I want to maximize the probability of getting my y over given, this means given x. For example, if I have sent sequence x, so what will be the maximum probability of getting my received sequence? What is y? Y is the received vector. Okay, as you can see, the sequence was x1 up till n, up till n plus l minus 1. So y was also up till n plus l minus 1. If you could see here, this was your y. This was the sequence. So what is the probability of maximizing this sequence with the knowledge that I knew what was sent? This is the optimization problem. So, but you know, if I want to detect a sequence, so this will become exponentially large with the block length. Yes, for example, greater size of the vector, you will need to see all the possibilities of the sequence. For example, at the first bit, let's say it could be 1. Second, let us say it could be 0, but it could also be 1. Then again 1 0 for all those 1 and 0 at the second part, and this way you can see that your tree will expand. And in order to cater for all the possibilities, this will become exponentially large. So an efficient algorithms need to exploit the structure of the problem. Yes, it has to be recursive, and so that is why this is the ubiquitous Viterbi algorithm. Now the ever present, very famous Viterbi algorithm, that is all not only recursive but exploits the structure of the problem. First of all, it establishes a finite state machine, and it defines at a time m the state of a machine is as follows. So in your machine, your state actually says that you have these many symbols. So state of the machine at mth is equal to x of m at the last, and then x of m minus 1 going up to x of m minus l plus 1. So this is a L size vector. For example, if I say I am sending BPSK symbols and I say that L is equal to 2. Alright, so you could see, so L is equal to 2 minus 2 plus 1. This will become minus 1. So it will be xm minus 1 and x of m. So there will be only two entries in your S. So you could see that your states will be L is equal to 2. So your states, and then number of states is 2 to the power L. M is the constellation size. So as BPSK is 2 symbols, so 2 to the power 2, there will be 4 total number of states. So you could see here, this is what he has shown. This is a state machine. So we say that our channel has a memory of 2, so it has and we are using BPSK symbols. Alright, so there are a total of 4 states. So what are those states? For example, one state is minus 1 plus 1. Now if in the next time slot I get a minus 1, so what will happen? This minus 1 will go to x of m minus 1, and the new will come to x of m. So new will come to x of m, old will go to here. So your state will switch from minus 1 plus 1 to minus 1 minus 1, provided you got a minus 1. Similarly, in this state, if I got a -1, so I have previously -1. Even if this -1 is ejected, this old becomes m-1, new becomes x of m, and again you can see that you have -1. So you will remain in this state. If you got a +1, so xm goes to +1, this remains -1. This state you get a +1, this gets +1, you get +1, and again you will remain in this state provided you are just getting +1. So you can form very well this finite state machine. So for example, if I had three symbols, meaning if I had, let us say, uh, BPSK symbols, not BPSK, but any other, let us say three, we don't have, let us say 4 PSK. In that case, we have four symbols, L is equal to 2. So you will have 4 to the power 2. So you will require 4 into 4, 16 different states. And you can see because you have four symbols, so one will be 0, 0, 0, 0, other will be 0, 0, 0, 1, and so on and so on till 1, 1, 1, 1. So you will have 16 different states. You can map 0 to -1 and 1 to +1. This is just irrelevant, just for explanation. So what is the receive symbol? So we know receive symbol, we have seen it is S, because you know what is S? S is the signal X of M, then -1 going up till L -1. Alright. Convolve with H means, as you have seen, summation H of L M with X of M minus L. So this will be S. So we have just summarized the previous notations. So you are actually convolving your H with your S vector. So each H will go with relevant S. So the optimization problem was maximizing y given x. So I can say it can be minimizing negative log y given s. This is a y vector, this is a s vector, but this is minus. So in minus, if I am minimizing, this means actually I am maximizing, because minimizing, I'm making it more smaller in terms of a negative number. You are minimizing. This means you are making it -4, -5, -6, -7, -8. But actually this log factor is becoming +4, +5, +8, +9. It is actually maximizing. So the maximization process can also be written as minimizing of minus log. So the constraint is there, and the second component of SM is the same as the first component of SM+1. So this symbol will, the second component of the of SFM, okay, will be the first component of SFM+1. So I think here he has made a mistake. This should be a vector here, S vector. So second component of SM is same as the first component of S vector m+1. S vector m+1. I think there is some mistake here. This should be m+1 and this should be m, and this S and S should be vector. So the second component of m+1 is actually the first component of S of m, as you have seen here, as you see, or here in the finite state machine. So I can break up this log expression as this provided the received symbols are independent. So the received symbols, if they are independent, they are not dependent on the other YFNs. So I can break up this product, okay, into probability, yani you can say joint probability of y1 this is equal to probability of y into probability of y2 y3 going up to yn. So you can see probability of y, and here actually this is multiplication, but because of log this becomes addition, so I can just add up. Actually joint is equal to product, but in log that product becomes addition, so you can also write it as follows. So we will be seeing it in a while, and again I have told you it has eaten up many steps, so you might not understand here, but it is a very summarized version, but you will try to go in detail when in from the other book the points that you have not understood. So this optimization problem, or in other words maximizing this, can be represented as a problem of finding the shortest path through the n-stage trellis shown in figure 3.16. So again you have not learned about this trellis. Maybe you might have done in your previous courses, but students would have not done, so I would go through it. So we will see in a while that maximizing this probability or minimizing them with negative actually is to find the optimum path to this trellis. Alright, so we will see in a while that the state sequence, that is we are going from, let us say, S1 state, then we go to S some other state at some other time, other state. So this is a vector itself. S is itself a vector which has all those x values. So I can transition from one vector to another vector depending on what I am getting. So this transition can be usually written as a path here. So we are here at this state, next time we are here, we might also here and here. In this way this trellis is formed, and we knew beforehand at what we are receiving, and then the cost of this transition is given as follows. So it is single value of YFM, not total addition. So, and the solution is given recursively. I know you all know what is recursive programming, so we won't go into detail. By the optimality of dynamic programming. So dynamic programming you might not have known. Those students who have studied algorithm, they will know. So dynamic says that, let us say that the cost of shortest path to the given state is this. Then the cost of shortest path for all the states can be computed by minimizing the cost from the m-1 to the mth stage, and then the optimum cost till m-1. Now what will be m-1? M-1 will be m-2 and cm-1. In this way, at the last step, your 0 will be your m1, let us say vm or v1 will be c1s. So you will say I will find the most optimum path in the first step. All the other paths will be calculated based on that optimum path. So at every stage, once we finalize our path, that will be the optimum path. So based on this fact, the shortest path to a state at stage m goes to this stage at stage m minus 1, then the path up to stage m minus 1 must itself the shortest path to state u. So going up to s at this stage, let us say in that path you have to go to this stage. The shortest path to this must be included in the complete path from for state S at stage M. This is the optimal. This is also shown in figure 3.7. Again, the book has not explained this in detail. So the path is here. So what he is saying that I want to go here. So I have two paths. One is this path, one is this path. So I will see what is the shortest path up till U. And this is the shortest path. The shortest path for S will be the shortest path for U combined with the path from U to S. Shortest path from U to S. This is what he is saying. So, and hence optimization problem is solved. It is also recursive because solution for one stage is equal to some constant plus the solution for the previous stages. But so we have a problem, and that problem is when the L size changes. And what is L? You know, L is the number of tabbed relay lines, number of multipaths in a frequency selective channel. Right? And M is the constellation size. But when L becomes very large, you can see the number of states, because you know states were given by this. For example, for BPSK, M was equal to 2 and L was equal to 2. So we just require 4 states. But if let us say I increase L, then even for BPSK this will become very, very large. So it becomes for very large. So there are other paths or other solutions for dealing with problems where L becomes large, because in that case Viterbi will not become practical. But again, yes, there are these zero forcing MMSE or DFE based maximum likelihood sequence directions. It's because they direct a full-fledged sequence, but they are never optimum. Viterbi is the optimum algorithm. So now again, I've told you this was very summarized explanation, and a lot of it will not be understood by you. Only I think those students will have understood who have gone through Viterbi algorithm in detail in any of the previous undergrad or maybe grad classes. So I will go through its detail just so that you won't find any difficulty here. So, so I will also upload this chapter so that you don't find any problems here. So this is a very simple channel. We have a sequence. All right. So let us say I apply some convolution code and I get another sequence. I modulate it, pass through this channel. So by the way, this is also included in the course, and I have changed the course outline, so this is also included. So let us say I demodulate my receive signal and I get another sequence. This goes to a convolution decode and I get my input sequence. So this figure we have seen, the figure in Proke's book was much better than the figure given here, but you can see that they are both actually equal. So you have this K-stage convolution encoder. These are the outputs, right? So you can get these outputs by modulo 2 sum of any of the inputs, and you can define your functions. So there are various ways to represent our encoder. So First is very simple. You just make a figure. Let us say this is 0, 0, 0. So first output is just sum of these 0, 0, 0. 0 plus 0, 0 is 0. So output will be 0. The second output is just sum of the first and the third bit. So 0 plus 0 is 0. But let us say if it is was 1, 1, 1. So first will be 1 plus 1, 2. So which is 0 in modulo 2. Then 1. So it will be 1. But this will be 1 plus 1. This will be 0. So you will get 1, 0 as the output. So you can see you're putting in one bit and you are getting two ports. So it is a 1 over 2 rate convolution decoder. And in this case, you can say it has 3 stages. Like this case equal to 1, 2, 3. And you can also define, uh, uh, connection vector as G1, which will be 1, 1, 1 because it was taking the input from all the three stages of your convolution encoder, while G2 will be 1, 0, 1. So you can calculate the output. Let us say if I feed 101, the message signal. So what will be the output? So step by step, you can put in it in the diagram. In this diagram, first let us say you have 0, 0, 0. Then 1 comes, so you will have 1, 0, 0, 0. What is the output? What is the output here? So for every input that is coming, you will be getting two outputs. So you will see the output sequence is 1, 1. So because once it is 1, it was all 0, 0. First bit 1 comes to be 1, 0, 0. But 1 is 1, 0, 0. 1 plus 0 is 1. And 1 plus 0 is 1. So both will give you 1, 1. So the first output corresponding to the first input bit 1, it will be 1, 1. Then this 1 will be shifted to the next and you will get a 0. So again calculate in this way until the last bit left, you will calculate and you will be getting this out. You can also calculate the impulse response of the encoder, and this can be done also not with difficulty. We just put 1. So we saw it was 1, 1. Then you have 0, 1, 0. 0, 1, 0. 0 plus 1 plus 0, it is 1. And 0 plus 0 is 0. All right. So you have found the impulse response by just putting 1 here, then shifting 1 here, then shifting 1 here. This is called the impulse response. The input sequence was 1, 0, 0. And the output was 1, 1, 1, 0 and 1, 1. So advantage is that once you know the impulse response, you can use it to find the output of any input sequence. So if I have 1, 0, 1, this is the impulse response. 0 is always 0, 0. 1 impulse response is again this. I will just shift them by 2 bits, add them, and by using modulo 2 sum, I will get the output convolution code. And you can diagram also to find the output. You can see here we have done the first part. Other part you can also do by yourself. So for every entry 0, 1, 0, 0 plus 1 plus 0 is 1, and 0 plus 0 is 0. So output will be 1, 0. First you will write the first function u1, then you will write the second function u2. There are also other representations which we also saw in the digital communication book of Pocase. For example, this one, that was in terms of D. So this is an old book. This represents in terms of X. So no problem, 1, because the first bit is going in the output. Second is coming, it is X, and third is X squared. Here only first and third, so it was 1 plus X squared. Again, you can find the output by just multiplying, mx with g1x. And this was your mx. Mx was 101, so this will be 1 plus 0 finished. So 1 plus x squared multiplied with this, you will get this output, this output. Then you can interlace these two outputs. So for 0, x0 you have 1 1, this will be 1 1 output. For x1 you have 1 0, this will be 1 0. Here you have 0 0, this will be 0 0, and hence you can also find the output like this. And famous is the state diagram which you also saw in our book. Achha, just one question. Can you view this book? Is this book visible to all of you? Hari, can you
Yes, sir.
all view this book? All right,
Yes,
very
sir.
good.
No, sir.
All right. Huh? Achha, now is it visible? Please see.
Yes, it is visible.
All right. So I was just saying here that yes, the other representation is of the famous state diagram, the finite state machine. And how can I represent them here? So, the basic concept for these machines is the Markov principle. That the next state depends only on the previous state. All the other previous states, they are irrelevant. Okay? The last previous state is important or depends only on the most recent state.